नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT जेईई एंड नीट। यह जेईई मेंस रिवीजन का 7th डे है और आज हम इक्विलिब्रियम पे दूसरा वीडियो बनाने जा रहे हैं। हमने इक्विलिब्रियम को दो पार्ट में डिवाइड किया। पहला था केमिकल इक्विलिब्रियम और दूसरा है आयनिक इक्विलिब्रियम। वीडियो शुरू करने से पहले मैं आपसे अनुरोध करूंगा कि अगर आप हमारे चैनल पे नए हैं और हमारे चैनल को सब्सक्राइब नहीं किया है तो प्लीज उसको सब्सक्राइब करें, और वीडियो देखने के बाद यदि आपको वीडियो पसंद आता है तो उसको लाइक जरूर करें। सो फ्रेंड्स, वीडियो शुरू करने से पहले मैं आपको बता दूं कि ये जेईई मेंस का डे 7 है और डे 7 का ये पार्ट 2 है। इट्स नॉट द पार्ट 2 ऑफ आयनिक इक्विलिब्रियम, इट इज पार्ट 2 ऑफ डे 7. सो व्हेन आई वाज गोइंग थ्रू द पास्ट ईयर पेपर्स, आई वाज फाउंड दैट मोस्ट ऑफ द 90% of the question was from solubility and solubility product. So I have decided to make a video on solubility and solubility product because the other questions which are coming is very simple and their number is less. So in this given time interval, it is better to discuss solubility and solubility product thoroughly. So the first thing about solubility and solubility product is there are many methods to represent solubility. In this chapter, when we are solving problems, there are three ways by which we are going to use this solubility. One is the mass of the solute in gram dissolved per liter of the solution. And the second way is the number of moles of solute dissolved per liter of solution. That is also known as molar solubility. And when we discuss about acid rain, for acid rain we use ppm parts per million, where it is defined as pressure of the gas upon total pressure into 10 to the power 6. So before starting that, there is a question, I think that is an objective question about acid rain, that during thunderstorm, if we calculate the pH of rainwater, it will be less or more. So during thunderstorm, the temperature will be very high. When the temperature will be very high, the atmospheric nitrogen will react with oxygen to form oxides of nitrogen like NO2, nitrogen dioxide, which is an acidic oxide. So when acidic oxide will dissolve in water, the H plus ion concentration in water, rainwater, is going to increase, and because of that the pH is going to decrease. So the answer was, during thunderstorm the pH of rainwater should decrease than normal condition when there is no thunderstorm. Okay, so let us start our video regarding solubility. So we know that saturated, we are studying equilibrium, right? So we are discussing saturated solution. We should not forget that it is saturated solution. Saturated solution means maximum amount of solute that can be dissolved at a given temperature in a solvent. So saturated solution can be obtained from soluble compounds, can be obtained from sparingly soluble compound. But it's more common that saturation will occur when the solute is sparingly soluble. And because of that, most of the time when we are discussing about saturated solution, we are discussing about sparingly soluble compounds. So AgCl is sparingly soluble in water. If nothing is mentioned, it is common sense that we have to assume that the solvent is water. So we have a saturated solution of silver chloride, and there is an equilibrium between AgCl in solid state and AgCl in aqueous state. The AgCl which is dissolved can dissociate to form Ag plus ion and Cl minus ion using the definition of degree of dissociation. That degree of dissociation is concentration of dissociated particles upon initial concentration. So initial concentration is S. From there we can find out what is the concentration of dissociated AgCl particles, that is S into alpha. So the amount of AgCl particles in aqueous medium left is equal to initial concentration minus concentration of dissociated AgCl particles. So from here we can write this equilibrium S alpha, because one particle of AgCl aqueous will dissociate, then one particle of Ag plus and one particle of Cl minus ion will form. So this is the equilibrium net reaction. If we add these two reactions, AgCl aqueous will cancel out. Generally, if nothing is mentioned about degree of dissociation of salt, then we have studied that salt are example of strong electrolyte. They are 100% dissociated. So most of the time, the degree of dissociation of the salt is equal to alpha. So alpha is 1. So we can say that this solid is in equilibrium with Ag plus in aqueous state and Cl minus in aqueous state. So the equilibrium constant of this reaction is equal to solubility product Ksp, which is equal to the concentration of Ag plus in equilibrium into concentration of Cl minus ion in equilibrium. Here the concentration of Ag plus when alpha is 1 is S and Cl minus is also S. So Ksp is equal to solubility square. So this is the general way. Most of the time alpha is 1, so we can write in this form. So what we have to remember that whenever we are discussing about solubility and solubility product, that is valid for saturated solution. Ksp is equilibrium constant and its value only depends on temperature. This concept in chemical as well as ionic equilibrium is used again and again. So here also when we are discussing solubility product or solubility, we are discussing that if temperature is constant, Ksp will remain constant. If we increase the concentration of Ag plus ion, then the concentration of Cl minus ion will decrease, or vice versa. So increasing concentration of one chemical species will decrease the concentration of other chemical species because their product of their concentration is equal to constant. So this is the thing which we have to keep in mind while studying solubility and solubility product. Relation between solubility and solubility product of some sparingly soluble compounds in their saturated solution. So these are typical examples where if we are not careful, we can do error. Like one example is saturated solution of Ki3. So Ki3 is there in solid state, and this solution is saturated with respect to Ki3. So Ki3 in aqueous, if nothing is mentioned, we'll assume that whatever dissolved is 100% dissociated. So we can write that K plus in aqueous state and I3 minus ion in aqueous state. So this is the right way. Some of the students in hurry, what they can do mistake that they can write that Ki3 is equal to K plus ion plus 3 times of I minus ion. So here charge is not balanced. This is incorrect. So be careful about that. So from there we can write that Ksp is equal to solubility square. This is one example where we have to be careful. Another example we can discuss saturated solution of calomel. Calomel is Hg2Cl2. So in Hg2Cl2, mercury is present in +1 oxidation state. When mercury is present in +1 oxidation state, it exists in the form of Hg22+. So if I write the reaction Hg2Cl2 in solid state is in equilibrium with Hg22+ in aqueous state plus 2 times of Cl minus ion in aqueous state, assuming alpha is 1, then we can say that if its concentration is S, it will be 2 times of S, and Ksp's concentration of mercurous ion into concentration of chloride ion whole square. If we put the value, we are getting Ksp is equal to 4S3. So these are these are two typical examples where we have to be careful. Otherwise, things are simple regarding writing the relation between Ksp and solubility, right? So factors affecting the solubility of sparingly soluble compound. There are 7 factors which can affect the solubility of sparingly soluble compound. I have used the word compound. Why? Because there are certain acids and certain bases which are sparingly soluble, right? Is most of the time when we are discussing about sparingly soluble compound, they are salt. But apart from salt, there can be acid and base. There can be other compounds which are sparingly soluble. So in place of salt, we have used sparingly soluble compound. So let me read these factors one by one. We are going to discuss. So the first factor is common ion effect. The second factor is simultaneous solubility. The third factor is effect of temperature. Fourth factor is effect of pH on solubility. Fifth factor is effect of complex formation on solubility, and the sixth factor is effect of hydrolysis on solubility, and the last factor is precipitation and preferential precipitation, which we are not going to cover because from the past year JEE mains exam we have find out there is no question based on that, and it is more important for JEE advanced, right, and less important for JEE mains. So we are going to cover all those points which are coming in JEE mains, right? So these 6 points are very important according to mains. One by one, we are going to cover it. So let us start with our first factor, effect of temperature on solubility. We know that when we are studying equilibrium constant, we are saying that the value of equilibrium constant with temperature depends that the reaction is endothermic or the reaction is exothermic. So if I am saying that if heat of solution is an endothermic process, then on increasing temperature, solubility will increase, because we know that Ksp is directly proportional to solubility. Higher the value of Ksp, more will be solubility. If the value of Ksp will be less, solubility will be less. So if the dissolution process is an endothermic process, so if we increase the temperature, solubility will increase or Ksp value will increase. So first, if they are asking that what is the effect of temperature on solubility, you should know that on dissolving the solute, it is an endothermic process or exothermic process. Like in thermochemistry, you have learned that when we dissolved NaCl, though NaCl is not sparingly soluble, but there can be a saturated solution of NaCl. So NaCl, when dissolved in water, dissolution of NaCl in water is an endothermic process. So on increasing temperature, solubility of NaCl is going to increase. Similarly, for sugar, when we dissolve sugar in water, it is an endothermic process. So on increasing temperature, solubility will increase. In general, in ionic equilibrium, when we are studying that in general ionic compounds dissolved in water, when ionic compounds dissolved in water or ionic salts dissolved in water, generally it is endothermic. So it's not always, but in generally it is an endothermic process. Based on the information given in past NCERT, I am discussing global salt, which is Na2SO4 dot 10H2O. So in old NCERT about the solubility, it is given that if we draw solubility versus temperature graph, on increasing the temperature, solubility of this salt in water is first going to increase up to 32 degrees Celsius. Up to 32 degrees Celsius, it is an endothermic process. And after 32 degrees Celsius, on increasing temperature, it is going to decrease. So after this, it is an exothermic process. When we analyze what is happening, so we found that solubility of hydrated salt in water is always endothermic. After 32 degrees Celsius, this global salt Na2SO4 dot 10H2O, on heating at 32 degrees Celsius, it will lose its water of crystallization. So 10 times of H2O in gaseous state. So now dissolution of Na2SO4 in water is an exothermic process. Dissolution of this is an exothermic process. Dissolution of this is an endothermic process. So till 32 degrees Celsius, when we are dissolving, it is hydrated salt. So on increasing temperature, solubility is increasing. At 32, it will lose all its water of crystallization, and dissolution of anhydrous Na2SO4 into water is an exothermic process. So this is given in NCERT. That's why we are discussing. So if you don't know that dissolution is endothermic or exothermic, don't comment that what will happen. If you know, then you know that if it is endo, then on increasing temperature, solubility will increase. If it is exo, on increasing temperature, solubility will decrease. Right? So this is about the first factor, effect of temperature on solubility. So you should also know that when strong base like NaOH, KOH, magnesium hydroxide, calcium hydroxide, when they are dissolved in water, they are exothermic reactions. So NaOH dissolved in water, KOH dissolved in water, it is an exothermic process. So on increasing temperature, the solubility of magnesium hydroxide, calcium hydroxide, sodium hydroxide, potassium hydroxide is going to decrease. The second factor is common ion effect. So due to common ion effect, the solubility of sparingly soluble compound will decrease. Let us try to discuss with the help of an example. So the first example is find solubility of calcium hydroxide in 0.1 molar solution of calcium nitrate. The Ksp of calcium hydroxide is 6.4 into 10 to the power minus 6 molar. So we have a solution. This solution is saturated solution of calcium hydroxide. So in saturated solution, this equilibrium will be there between solid and dissolved part of calcium hydroxide. So here it should be, this is calcium hydroxide. So there is an equilibrium between calcium 2 plus ion and 2 times of OH minus ion. And in this solution, this is a soluble salt, because when you go through NCERT, they have mentioned that if the solubility is less than 0.01 molar, then it will be sparingly soluble. If the solubility is greater than 0.1 molar, then it will be soluble compound. So calcium nitrate is soluble compound, and this is the solubility in saturated solution, right? So here this solution is not saturated with respect to calcium nitrate, just the concentration of calcium nitrate is given, that is 0.1 molar. So if we write, if nothing is mentioned about this salts are example of strong electrolyte, they are 100% dissociated. So this is 100% dissociated. Here also, if a substance is sparingly soluble, alpha does not depend on solubility. So calcium hydroxide, whatever dissolved, is 100% dissociated. We are assuming that. So degree of dissociation is not related with weak or strong, having weak solubility or strong solubility, more solubility or less. It is sparingly soluble or more soluble. Degree of dissociation is nothing to do with that. So now, at equilibrium, if I write that, what are the concentration of different chemical species in this system? There is calcium hydroxide in solid state, and when it will dissolve, it forms some calcium 2 plus ion. So this is S, then this OH minus will be 2 times of S, where S is the solubility of calcium hydroxide. This is a salt. Salts are example of strong electrolytes. So in the solution, it does not exist. It is 100% dissociated. On dissociation, its concentration is 0.1. So 0.1 mole of calcium 2 plus ion, and this is 0.2 molar nitrate ion will be there. Since calcium 2 plus ion is common, so we'll write the net concentration of calcium 2 plus ion in this whole system. So that is equal to 0.1 plus S. And since we are not changing the temperature, nothing is mentioned about temperature, so the value of Kvpy is not going to change. So we can write that the value of Kvpy is 6.4 into 10 to the power minus 6, which is equal to S plus 0.1, which is the concentration of calcium 2 plus ion, and concentration of OH minus ion is equal to 2S whole square. Now, since it is a sparingly soluble compound, Kvpy is very less, equilibrium constant is very less, means this reaction in moving in forward direction will be less. And there is a common ion effect from calcium nitrate. Calcium 2 plus is mainly coming from this calcium nitrate. So assuming that this Kvpy is very less, so the reaction moving in forward will be very less, and there is common ion effect. Because of that, we can take an approximation that the value of S is very small with respect to 0.1. After calculating, we'll check that our assumption is correct or not. So if we take that approximation, we can write here that this value is equal to 0.1 4S square, 6.4 into 10 to the power minus 6. From here, if I simplify, I can write that the value of S is equal to under root of, if we simplify here, we can write that this is 16 into 10 to the power minus 6. If on further simplification, we can write that this value is equal to 4 into 10 to the power minus 3. So this is the value of S. Now this value is 0.004 and this value is 0.1. If we say that the bigger value is 20 times or more than the smaller value, we can neglect the smaller value with respect to bigger value, right? So that's why our assumption is correct. We can neglect the value of S with respect to 0.1. So this is the solubility, 4 into 10 to the power minus 3. If this calcium nitrate is not in this solution, then we can directly apply the formula and we can write that Kvpy is equal to 4S cube. Kvpy is equal to 1.6.4. Kvpy is equal to 6.4 into 10 to the power minus 6, which is equal to 4S cube. So from here, if I simplify, this value is equal to 16 into 10 to the power, or 1.6 into 10 to the power minus 6. So this is S cube, and from there, if I calculate what is S is equal to cube root of 1.6 into 10 to the power minus 2. The value of 1.6, if it is mentioned, we'll get this value cube root of 1.6 is definitely greater than 1. So this is of the order of 10 to the power minus 2. While because of common ion effect, now the solubility is of the order of 10 to the power minus 3. So we can say that due to common ion effect, the solubility is going to decrease. Let us take another example to discuss the same point. Calculate solubility of calcium hydroxide in first part is saturated solution of calcium hydroxide, and the second part is 1 molar solution of NaOH. The Ksp of calcium hydroxide is given and the value of cube root of 1.6 is given. So the first part, in saturated solution, we can directly apply the formula that Ksp is equal to concentration of calcium 2 plus ion, which will be as concentration of OH minus, which will be 2s whole square. From there we can write that 4s cube is equal to Ksp, and if we put the value from there, we can write that solubility is equal to Ksp. Ksp is 6.4 into 10 to the power minus 6 divided by 4. So on solving, we are getting that 1.6 to the power 1 by 3 into 10 to the power minus 2. On further simplification, we are getting that 1.17 into 10 to the power minus 2. This is the solubility. Already we have solved in the last question. This is the solubility in saturated solution of calcium hydroxide. There is no other chemical species, only calcium hydroxide is there. But now in this question, they are saying that solution is now having sodium hydroxide along with calcium hydroxide. So there is a saturated solution of calcium hydroxide. CaOH whole twice in solid state is in equilibrium with calcium 2 plus ion in aqueous state plus 2 times of OH minus ion in aqueous state. If I write at equilibrium, this solid form is there in this system. Calcium hydroxide is there in solid state and some part is dissolved. Whatever dissolved is 100% dissociated. So we can say that S and 2 times of S. This is at equilibrium if only calcium hydroxide is there, but in this system sodium hydroxide is there. It is a strong base. It is 100% dissociated. So it will form Na plus in aqueous state plus OH minus ion in aqueous state. So if we put 1 molar NaOH, there is no NaOH in molecular form. All will dissociate. It will form 1 molar Na plus ion. And 1 molar OH minus is coming from NaOH, and S amount, 2S amount is coming from calcium hydroxide. So from here we can write that 1 plus 2S. Again the logic is, since calcium hydroxide is sparingly soluble, Ksp value is very small, means this reaction is moving in forward direction by a small amount. And because of this OH minus coming from NaOH, there is common ion effect. Because of this common ion effect, this reaction will further go in backward direction. So we can take an approximation. We can approximate that the value of 2s is very small with respect to 1. After taking approximation, we'll solve and we'll cross check that our assumption is correct or not. So again here, if I put the value of Ksp is not going to change because we are not changing the temperature. So 6.4 into 10 to the power minus 6. Concentration of calcium 2 plus ion in this system is equal to solubility of calcium hydroxide. And OH minus whole square, OH minus we can write 1 plus 2s, but we can neglect 2s with respect to 1. So we are taking approximation here. So 1 ka whole square. So from there we are getting that the solubility is equal to 6.4 into 10 to the power minus 6, which is very small with respect to 1. So our assumption is correct. While there are two numbers, one is bigger number, other is smaller. We are saying that if bigger number is 20 times or more than the smaller number, then we can neglect the smaller number with respect to the bigger number. So you can see here that because of common ion effect, the solubility of sparingly soluble compound is going to decrease. So very common question, very simple question. You can give time while solving the question. Don't do in hurry, you will get the marks. Now the third factor is simultaneous solubility. Like here an example. This solution is saturated solution with respect to calcium carbonate, and this is also saturated solution with strontium carbonate. So in this system, there are two equilibria. This is an example of simultaneous equilibrium. According to simultaneous equilibrium, if two and more reactions are taking place in the same system, right, and these are reversible reaction, then at equilibrium we'll say that it is simultaneous equilibrium. So now if I write that initially this solid is there, calcium carbonate is there, and this solution is saturated, means some part of this calcium carbonate will dissolve. So solubility of this calcium carbonate we can assume S1. So S1 here and S1 here. At time t is equal to 0, this solution is also saturated with respect to strontium carbonate. Some part of it will dissolve. It will dissolve, its solubility will be S2 and S2. So here, because carbonate ion is coming from both source, so we can write that at equilibrium the concentration of carbonate ion is equal to S1 plus S2. So this is the concentration of carbonate ion at equilibrium. We are discussing at equilibrium. When equilibrium is not established, S1 and S2 are variable. Once equilibrium is established, then the value of S1 and S2 is fixed. So we can say that this is the first equilibrium constant Ksp1. This is the second equilibrium constant Ksp2. We can write that the value of Ksp1 is equal to concentration of calcium 2 plus ion, that is S1, into carbonate ion concentration S1 plus S2. Same way we can say that Ksp2 is equal to S2 multiplied by S1 plus S2. So if I add these two, we can write that the value of Ksp1 plus Ksp2 is equal to S1 plus S2 whole square, and from there we can find out what is the concentration of carbonate ion. So this is the concentration of carbonate ion. Now there is a question, they can ask an objective question that due to this simultaneous solubility, if there is a common ion in both chemical species, so due to this common ion, the solubility of calcium carbonate as well as strontium carbonate is going to decrease, because both reactions are moving in forward direction because of this carbonate ion. For this reaction, some extra carbonate is coming, so it is moving in backward, and same for the second reaction, some carbonate ion is coming from the first reaction, that's why it is moving in backward direction. So important point in objective, they can ask that due to common ion effect in simultaneous solubility, what is the effect on solubility? So solubility of both the chemical species is going to decrease due to common ion effect. So we can take another example of simultaneous solubility. So here there is a saturated solution of calcium hydroxide as well as magnesium hydroxide. So this solution is saturated with respect to both. So if I write that, what will happen at equilibrium? At equilibrium, this solid is there, and the solubility of this solid, if I am assuming that is S1, then this is equal to 2 times of S1. Same way we can write for the other. Magnesium hydroxide is there, so when it will dissolve, its solubility is S2, so this is 2 times of S2. Since OH minus ion is common and it is coming from both sources, so the net concentration of OH minus in the system is equal to 2S1 plus 2S2. Here also we should write 2S2 plus 2S1. The equilibrium constant for this reaction is Ksp1. The equilibrium constant for this reaction is Ksp2. So we can write now that Ksp1 is equal to concentration of calcium 2 plus, that is S1. OH minus whole square means 2 times of S1, 2 times of S2 whole square. Same way we can write that Ksp2 is equal to S2, 2 times of S1 plus 2 times of S2 whole square. Again, if we add these two, we can write that Ksp1 plus Ksp2 is equal to 4 times of S1 plus S2 whole cube. And in this way, we can calculate what is the concentration of OH minus ion. So from here, I can write that S1 plus S2 is equal to Ksp1 plus Ksp2 divided by 4 to the power 1 by 3. And if I multiply the whole thing by 2 on the left hand side and right hand side, then we can write that this is the concentration of OH minus in this system. So same way we can solve, right? Depending upon a stoichiometry of these salts, we have to solve and find out what is the concentration and what is the effect. So here also I can say that due to common ion effect, the solubility of both salts is going to decrease. The fourth factor is effect of pH on solubility, and it is the most important factor. There are many good questions based on this. So we are starting with the first factor or first type of question asked regarding effect of pH on solubility. So let me read the question. Example 1. What is the molar solubility, means molarity, of magnesium hydroxide in a buffer solution of pH 9? Ksp of magnesium hydroxide is equal to 1.8 into 10 to the power minus 11. So we have a saturated solution. It is not mentioned in the question. It is a common sense that when we are talking about equilibrium, solution must be saturated. So solution is saturated with respect to magnesium hydroxide. Apart from magnesium hydroxide, there is a buffer solution. Not mentioned that this buffer is of what, but there is a buffer solution, and the property of buffer solution is the change in pH is very small, means pH is almost constant in this solution. If we add something, on adding something, there is no change in pH. Here we are not adding, so pH they have given that pH of this buffer solution is 9. We know that if nothing is mentioned about temperature, temperature is room temperature. At room temperature, pH plus pOH is 14. From there we can find out what is pOH of the system. pOH of the system is 5. So OH minus ion concentration in the system is 10 to the power minus 5. We know that the value of equilibrium constant Ksp only depends on temperature. We are not changing the temperature, so we can use the concept that Ksp value for magnesium hydroxide can be written as concentration of magnesium 2 plus ion into concentration of OH minus. They have given pH of solution, so we know what is concentration of OH minus, that is 10 to the power minus 5 whole square. Ksp value they have given, that is 1.8 into 10 to the power minus 11. So on solving from here, I can write that the concentration of magnesium 2 plus ion is equal to, if I simplify, this is 10 to the power minus 10. So 10 to the power minus 1 will be left. If I simplify, this value is coming 0.18 capital M. So this is the solubility of magnesium hydroxide. If this buffer solution is not there, what will happen? If this buffer solution is not there, the solubility should be 4s cube is equal to Ksp. And from there, if I simplify and solve this value, definitely that value will be less than 0.18, because if this buffer solution is not there, and if I am solving the solubility, already I have solved here, if I am saying that solution is saturated only with respect to magnesium hydroxide, then solubility is of the order of 10 to the power minus 4. So this is the value of solubility, and OH minus ion concentration is 2 times of solubility, so OH minus will be this value. Now here, if I am calculating, magnesium 2 plus is of the order of 10 to the power minus 1. So definitely here, because this buffer solution is basic in nature, there is common ion effect. Because of common ion effect, the solubility of magnesium hydroxide, let me check that it is common ion effect or it is consumption of OH minus here. Okay, so from here we are getting that the solubility of magnesium 2 plus ion is equal to 0.18. Solubility is increasing. If it is only magnesium hydroxide, solubility is of the order of 10 to the power minus 4. Now the solubility is of the order of 10 to the power minus 1. Moving to the second example of effect of pH on solubility, let us move to the second example. Effect of acid rain on historical monuments made up of marble. So the example in India is Taj Mahal. We are discussing that why there is corrosion of Taj Mahal. So Taj Mahal is made up of marble. So chemically it is calcium carbonate. So calcium carbonate in solid state is in equilibrium with calcium 2 plus ion in aqueous state and carbonate ion in aqueous state. In this, the anion carbonate ion is an anion of weak acid, carbonic acid, H2CO3. The anion of weak acid is carbonate ion. So if I am adding, we know that if the acid is weak, its conjugate base is strong. So when we are adding H plus, what will happen, that this carbonate ion will accept H plus and it will form bicarbonate ion. The equilibrium constant of the first reaction is Ksp. For the second reaction, the value of equilibrium constant is 1 upon Ka2. Because when HCO3 minus will dissociate, it will form carbonate ion and H plus. It is reverse of that, so 1 upon Ka2. Again, if HCO3 minus is formed and excess of H plus is there, it will again combine to form carbonic acid. So here again equilibrium constant of this reaction is equal to Ka1. So assuming that since it is a sparingly soluble, carbonate ion is very less, so H plus is more with respect to carbonate ion. So this reaction is going to completion. All the carbonate is now existing in bicarbonate form, and all the bicarbonate is now converted into carbonic acid. So when I am writing at equilibrium, this is calcium carbonate in solid state. Here we should write the solubility as S, and here it will be S. Now this whole carbonate ion, because here suppose if I am starting with a concentration of H plus ion, so this reaction is going to completion because the value of equilibrium constant is very large. The value of Ka1 for carbonic acid is 10 to the power minus 7, and the value of Ka2 for carbonic acid is 10 to the power minus 11. So 1 upon Ka2 means 10 to the power 11. When the value of equilibrium constant is very large, reaction will complete in forward direction, equilibrium will establish from backward direction. Because of that, all the carbonate ion is converted. Here I am writing here this is equal to S. Whatever here it was, it is converted into this, and then we'll say that equilibrium will establish from backward direction. When we are writing equilibrium will establish from backward direction means S minus X. I am neglecting that X because reaction going in backward direction very less. Here also I have write A minus S plus X. I'm neglecting X with respect to A minus X S, and this will be X. So here it will be X, and for this reaction whatever this S was there, this S is now going to completely react. So already A minus S was there, and this S further going to completely react. So I have to write A minus 2S. Here also I have to write A minus 2S, and this now I will say that this is completely converted into carbonic acid. So this will be S, this will be S, and equilibrium will establish from backward direction. So S minus Y, this will be A minus 2S plus Y, and this will be Y. So Y and Y, right? This is the concentration of different chemical species at equilibrium state. If I add all these three reactions, the equilibrium constant for this net reaction is equal to KSPA. KSPA is the solubility product of sparingly soluble compound in acidic medium. For this particular example, that is equal to KSP divided by Ka1, Ka2. And if we write in the net reaction concentration, this solid will be there at equilibrium. The concentration of H plus, if initially it is A, it will be A minus 2 times of S, where S is the solubility of calcium carbonate. All the calcium 2 plus ion is coming from calcium carbonate, so this is equal to S, and all the carbonate ion is now existing mainly in the form of carbonic acid, so this will be S. So using this I can write that KSPA is equal to solubility square upon A minus 2 times of S whole square. From there we can solve. If we know KSP, Ka1, Ka2 and A, we can find out what is the solubility of calcium carbonate in acidic medium. And this is the reason for corrosion of Taj Mahal due to acid rain, and it's a great concern. So based on that, let us practice. This is also the same question. In place of calcium carbonate, we have taken some metal sulfide. So solubility of metal sulfide in saturated solution of H2S. In saturated solution of H2S, the concentration of H2S is equal to 0.1 molar. So its concentration is 0.1 molar, can be represented by this. So this is the equilibrium. They are saying that this basically, if I explain here, metal sulfide in solid state is in equilibrium with metal 2 plus ion in aqueous state plus sulfide ion in aqueous state. Again here the metal sulfide ion is an anion of weak acid H2S. So when we add H plus ion, this sulfide ion will combine with that H plus ion and it will form HS minus. Again, the equilibrium constant of the first reaction is Ksp of this metal sulfide. Equilibrium constant of this reaction is 1 upon Ka2, and Hs minus will further combine with H plus ion, and equilibrium constant of this reaction is also very large, which is 1 upon Ka1. So from here we can write that this value is equal to H2S. Same way, if I write that what is the overall reaction, so on adding these reactions we'll get the reaction given over here. Metal sulfide plus 2 times of H plus will form metal 2 plus ion plus H2S in aqueous state, right? So this is in solid state, and other chemical species are in aqueous state. So now this is Kspa, this equilibrium constant is Ksp, whose value is equal to Ksp divided by Ksp divided by Ka1 and Ka2, Kspa, right? So now let us read the question. The value of equilibrium constant is given for few metal sulfide. If concentration of each metal ion in solution is 0.01 molar, which metal sulfide are selectively precipitated at total H plus? They have given what is the total H plus ion concentration at equilibrium in a saturated solution of H2S. For such reaction, like this is the reaction, this is the solid on the left hand side. So if we say that the reaction is moving in backward direction, then we'll say that precipitation of this solid will take place. So precipitation of solid will take place when the reaction will move in backward direction. For the reaction to be moving in backward direction, we know that the reaction quotient should be greater than the equilibrium constant. So the value of equilibrium constant for different type of metal sulfides they have given, like for MnS, the equilibrium constant is 3 into 10 to the power 10. For ZnS, it is 3 into 10 to the power minus 2. For cobalt sulfide, it is 3, and for PbS, it is 3 into 10 to the power minus 7. So if I calculate that in this system, what is the reaction quotient for this reaction, overall reaction? Reaction quotient for this reaction is concentration of metal 2 plus ion in the system, concentration of H2S in the system, upon concentration of H plus ion in the system whole square. They have given that all metal ion have the same concentration, that is 0.01, and all are present in saturated solution of H2S, so its concentration will be 1. And in all these systems, the H plus ion concentration is equal to 1. For all these solutions, we are getting that the reaction quotient is 10 to the power minus 3. Now we have to check that this reaction quotient is greater, it should be greater than equilibrium constant. So we are getting that in this PbS, in case of PbS, we can say that the value of reaction quotient is greater than equilibrium constant. So we can say that PbS will go in backward, this equilibrium will go in backward, and if it will go in backward direction, it will form the precipitate. So PbS will form the precipitate. This is the third example, very common in exams. So already I think this example is asked in JEE Advanced, right? So let us discuss this. Calculate solubility of AgCN in a buffer solution of pH 3. So there is a buffer solution whose pH is 3, and AgCN Ksp is given, means AgCN we have a saturated solution. The Ksp of AgCN is 4 into 10 to the power minus 16, and the dissociation constant of the acid is very small, means Cn minus is an anion of weak acid. So effect of pH on solubility means in this solution, if we are solving, we have a solution in which there is a saturated solution of AgCN. So we can write that AgCN in solid state is in equilibrium with Ag plus ion in aqueous state plus Cn minus ion in aqueous state. So if we write that at equilibrium, this will be S and this will be S if there is no other chemical species in the system, but they are saying that there is buffer solution. Because of that buffer solution, pH is 3. pH is 3 means H plus ion concentration is 10 to the power minus 3. So in this system, the solution is acidic in nature. The system has H plus ion whose concentration is equal to 10 to the power minus 3. So because of this concentration of H plus ion, since it is sparingly soluble, the concentration of Cn minus ion should be smaller. If this buffer is not there, we can apply formula solubility square is equal to Ksp. So solubility is under root Ksp. So 2 into 10 to the power minus 8. So obviously, since it is sparingly soluble, the Cn minus coming from this salt is very small. But now, because of this H plus ion, whatever the Cn minus ion is there, that Cn minus ion will combine with this excess amount of H plus ion to form HCN. So the equilibrium constant of this reaction is 1 upon Ka, and the equilibrium constant of the first reaction is Ksp. And if I add these two reactions, I can write that AgCN in solid state plus H plus ion in aqueous state will form Ag plus ion in aqueous state plus HCN in aqueous state, right? So here this Cn minus will react completely and it will convert into HCN. So from backward direction, this Cn minus will be produced. So if I am saying that since it is a buffer solution at equilibrium, I can write that since buffer solution pH change will be very small, so H plus will remains almost same, 10 to the power minus 3. And this Cn minus is now mainly existing in the form of HCN, whose value is equal to S. And equilibrium for this reaction will establish from backward direction. S minus X, X is very small, neglected. X I am neglecting with respect to H plus ion also, but Cn minus concentration will be X. So from here, if we simplify that, what is the value of equilibrium constant for this reaction? That is equal to Ksp divided by K, that is Kspa. If we put the value for AgCN, this value is 4 into 10 to the power minus 16, and the value of K is 9 into 10 to the power minus 10. That is equal to, if I put the value, this solid is there, this is 10 to the power minus 3, and this will be S and S. So we can write solubility square upon this value is equal to 10 to the power minus 3. So on solving, we are getting that solubility square is equal to 4 by 9. This is 10 to the power minus 9. So on further simplification, we can write that solubility is equal to 2 by 3 times of under root 10 into 10 to the power minus 5. So this is the solubility. So you can check that if there is no buffer solution, the solubility of AgCN is 2 into 10 to the power minus 8. Solubility square is equal to Ksp. Solubility is under root Ksp, 2 into 10 to the power minus 8. But from 2 into 10 to the power minus 8, it is raised to 10 to the power minus 5, right? So 1000 times, almost 1000 times solubility is changed because of effect of pH on solubility. Now the fifth factor, this is also very important, effect of complex formation on solubility. So nowadays we are using digital camera, but before that we are using a camera in which a reel is there, and we do photography using black and white photo film, right? So there is a concept of complex formation. With the help of that, we are going to increase the solubility. So let us go through that complex formation concept. So here what is happening, that this is a camera, and we know that if I have to take picture of this person, the light should come from this direction so that it can incident on the face of the person and reflect back, and the camera person should be here. So when this is the situation and this camera person is clicking the light, there is a film, photographic film, this reflected light will incident on that, and because of that there is a chemical reaction. So this photographic film is made up of cellulose paper on which there is a coating of silver bromide. So when this light will incident on that, so silver bromide will participate in a redox reaction. Silver bromide, silver is present in +1 and Br is in -1. Due to incidence of photon, silver in +1 is reduced to silver metal, and Br minus is converted into Br2 gas. So this silver, because one photon will interact with one molecule, so this silver is going to form, this reaction is happening, so silver atoms are forming. So this silver will form in powdered state. When silver is in metallic form, it has metallic luster. When silver is very fine, it is in powdered form, it is black in color. So this face, round face of this person is here, that is black in color, and the part which is not exposed to light will have silver bromide. Now if I bring this whole film into light, this silver bromide, this yellow color thing will also become black. So in black I will not able to find his round face. So what will happen, that before removing this film into light, we have to remove this silver bromide, and silver bromide is sparingly soluble. So in order to dissolve silver bromide, we are using ammonia solution, because in normal water the solubility of silver bromide is less. So the concept here is the effect of complex formation. This AgBr is going to form complex with ammonia. So here is the concept: AgBr in solid state, when dissolved it will form Ag plus ion and Br minus ion. Since this Ag plus, because ammonia is there in the solution, Ag plus is central atom, it will combine to form complex, and this complex, linear complex, is very stable. So more will be the stability, more will be the equilibrium constant of this reaction, that is known as formation constant. Formation constant means central atom and ligand will combine to form ionic complex. So the equilibrium constant of that reaction is known as formation constant. For this reaction, first reaction, equilibrium constant is known as solubility product. So again here, if we write the things, this is solid and some part of this is going to dissolve. So here it will be S and this is S. Br minus is not participating in the reaction, so it will remain S. But since in the medium there is ammonia, its initial concentration is A. So because this equilibrium constant is very large, this reaction will complete in forward direction. So all the Ag plus is now existing in the form of this complex ion. So here it is S, and here it will be A minus 2 times of S. And the equilibrium will establish from backward direction. So here we should write S minus X plus 2x, x neglected. So here we should write this is X and this is X. So this is the net equilibrium concentration of all the chemical species in this equilibrium. So finally I write that in this reaction the concentration of ammonia is A minus 2 times of S, and the complex ion will be S and Br minus ion will be S. The equilibrium constant, that is Ksp into K formation. We are adding these two reactions, so equilibrium constant will multiply, which is equal to solubility square upon A minus 2 times of S whole square. So from there we can solve, we can write that S A minus 2 times of S is equal to under root K formation into Ksp. The value of K formation, Ksp and A is given. From there we'll get the solubility. So again here, since Ag plus ion is consumed in the second reaction, this reaction will move in forward direction according to Le-Chatelier principle. So because of complex formation, the solubility of sparingly soluble compound can be increased. So let us discuss one more example. Based on that, the concept is same. So here is the example: in black and white film developing, excess of AgBr is removed from the film negative by hyposolution. Hyposolution is Na2S2O3 solution through the formation of complex ion. This is the complex ion. Calculate solubility of silver bromide in 1 molar hyposolution. K formation of this complex ion is 5 into 10 to the power 13, and Ksp of silver bromide is 5 into 10 to the power minus 13. So again here, in place of ammonia we are using hyposolution. So we can say that in this system there is silver bromide, saturated solution of silver bromide. AgBr in solid state is in equilibrium with Ag plus ion in aqueous state plus Br minus ion in aqueous state. Because of this thiosulfate ion, Ag plus ion in aqueous state will form a complex with thiosulfate ion in aqueous state, and this complex ion is stable, means equilibrium constant of this reaction is very large. It is given 5 into 10 to the power 13. So we can write the complex ion is AgS2O3 twice 3 minus ion in aqueous state. So again, if I add these two reactions and write, the net reaction is AgBr in solid state plus 2 times of thiosulfate ion in aqueous state will form this complex ion in aqueous state plus Br minus ion in aqueous state. So this solid will be there at equilibrium initially, whatever the concentration of thiosulfate ion is there, minus 2 times of S, because all the Ag plus is converted into this complex ion. So here it will be S and this will be S. So now if I put the value and simplify, equilibrium constant is K formation into Ksp. So Ksp into K formation is equal to S A minus 2 times of S whole square. So if I simplify, I can write that S upon A minus 2 times of S is equal to, if I multiply K formation and Ksp value, it is 25. 10 to the power plus 3, 13 and minus 13 will cancel out. So under root of that will be 5. Cross multiply it, I can write that this is equal to 5 times of A and this is minus 10 times of S. So 11 times of S is equal to 5 times of A. The value of A is given, right? It should be given 1 molar hypo solution. So A is 1. So from there we can write that solubility is equal to 5 by 11 mole per liter. So this is the solubility. And if you can check that, if this thing is not there, only AgBr is there, then we can write that Ksp is equal to solubility square, right? So here in this solution hypo is there, if only there is a solution of AgBr, then we can write directly that solubility square is equal to Ksp, or solubility is under root Ksp. So solubility is of the order of under root 50 into 10 to the power minus 7 capital M, means approximately 7 into 10 to the power minus 7 capital M. This is the order of solubility. Now from this value, it is increased to this value, right? So there is a huge change in solubility due to complex ion formation. So this is very important effect of complex ion formation on solubility. And the last factor is effect of hydrolysis on solubility of sparingly soluble compound. So through an example, we'll try to understand it. pH of a saturated solution of silver salt of monobasic acid Ha is found to be 9. Find the Ksp of sparingly soluble salt Aga. So here in the question, they are saying that there is a sparingly soluble salt Aga, which is a salt of Ag plus ion and A minus ion. A minus ion is anion of weak acid. So when we write equilibrium, Aga in solid state is in equilibrium with Ag plus ion in aqueous state plus A minus ion in aqueous state. If nothing is mentioned about pH, that if it is not mentioned that pH is 9, we don't consider anything and we can directly write that Ksp is solubility square. But they are saying that the pH of this solution is 9, and they are not saying that anything else or buffer or something is there, only Aga solution is there and pH is 9. How can you justify that this solution is basic in nature? They have given the data that anion is of weak acid, so we have to consider hydrolysis of this anion, otherwise there is no way to find out or justify why the pH is 9. There is no buffer solution into it. They have given and they have mentioned that it is an ion of weak acid because acid Ka is 10 to the power minus 10. So this is a hint to consider that while solving the question, we have to consider the hydrolysis of an ion of weak acid. So if we consider, we can write A minus into concentration of H2. A minus is interacting with water. It is taking H plus from water to form Ha in aqueous state and OH minus ion in aqueous state. So at equilibrium, this solid will be there, and the solubility of this solid is represented by Ag plus ion. Initially, this will be S. Now, because of this reaction, if I write that, what is the hydrolysis constant of this reaction? So hydrolysis constant of this reaction is equal to Kw upon Ka, because you can write that this is equal to concentration of Ha, concentration of OH minus upon concentration of A minus. If I multiply the numerator and denominator by H plus ion, then H plus ion into OH minus, this value is Kw, and concentration of H plus A minus upon Ha is equal to K. So if I put the value here, 10 to the power minus 14 divided by Ka value is 10 to the power minus 10. So this value is 10 to the power minus 4. So you can write here, this is S minus X, this will be S minus X. This is pure substance, almost solvent, so I'm not writing anything. This is equal to X and X. And they have given the value of OH minus, because they are saying that pH of this solution is equal to 9, means pOH of this solution is equal to 5, means OH minus ion concentration, we know that is 10 to the power minus 5. So we know the value of X, that is 10 to the power minus 5. With the help of this value, I can calculate the value of S minus X, because I can write that KH is equal to 10 to the power minus 4, which is equal to X square upon S minus X. S minus X. X square is 10 to the power minus 10. So S minus X. From here I can write that the value of S minus X is equal to 10 to the power minus 6. And we can calculate what is S. S is equal to X plus 10 to the power minus 6. The value of X is equal to 10 to the power minus 5. So minus 5 plus 10 to the power minus 6 is, if I simplify this, I can write this is 0.1 into 10 to the power minus 5. So 1.1 into 10 to the power minus 5. So this is the value of S. And they are asking that what is the KSP? What is the KSP of this salt? So KSP of the salt means concentration of Ag plus ion into concentration of A minus ion. And concentration of Ag plus ion is S, and the value of S we have calculated 1.1 into 10 to the power minus 5, and the value of A minus ion concentration is S minus X, which is 10 to the power minus 6. So if we simplify, we'll get that the KSP value is equal to 1.1 into 10 to the power minus 11. Right, so this is the best question regarding hydrolysis. So what is the conclusion? If the salt has anion of weak acid, and due to hydrolysis of anion of weak acid, this anion is going to decrease. So according to Le-Chatelier principle, the reaction will move in forward direction, because of which the solubility of sparingly soluble compound is going to increase. Once more, I want to discuss here that, because there was a question where the pH is 3, and they have said that in that question that we have added a buffer solution. So AgCN, or like AgA, we can say here, right? AgA, if there is a buffer solution and pH is 3, then it is effect of pH, right? So here there is no buffer solution, and they are saying that this is an anion of weak acid and pH is 9. How you can justify? You can justify by considering hydrolysis of anion only. So don't confuse. If this pH is not given, this Ka data is not given, it means that you have to solve the question normally. Ksp is equal to solubility square. So these are the 6 factors which affect the solubility. We are not going to discuss about precipitation or preferential precipitation. That is not that useful for JEE mains. So friends, what I am saying that whatever important according to JEE mains I have discussed. So most 90% of the question is coming from solubility and solubility product, because they have a constraint. From the whole equilibrium chapter, they have to ask one question only. And that one question either they can ask from chemical equilibrium, or they can ask from ionic equilibrium, and whatever they are finding in the entire chapter, which is the most important topic, that is solubility and solubility product. So very simple questions based on solubility and solubility product will come from ionic equilibrium. Don't afraid of equilibrium, because the type of questions which are coming is very simple. If you revise these points, right, you will find that all the questions, almost 90% questions are coming from here. तो यदि आपको ये वीडियो अच्छा लगा तो प्लीज इसको लाइक करें,